So this video is a continuation of the previous 3 videos. This is a problem session which is devoted to Lagrangian mechanics, and we are going to look at a simple problem at first. If you remember that mass spring problem I did in the previous video, well, that was very simple. Now we are going to do a damped oscillator, like a mass attached to a spring and the thing is kept in a viscous medium, a real world problem. So as you are familiar from Newtonian mechanics that you know how to draw free body diagrams, and that is how we get those equations of forces and we solve, and to get that equation of motion there is one differential equation. Anyway, that was something we learned in high school, and in this video we are going to look at how we do those type of problems by using the Lagrange method, mainly Lagrangian mechanics, and we are going to apply this powerful tool, the Euler-Lagrange, here to show or illustrate you how we solve problems. So without any more talking, let us start with our first problem of this problem session. So it's basically a mass spring, and that is something like this. Say this is our ceiling, fixed rigid support, and then with the help of a string you suspend a mass and this thing is kept in a viscous medium of constant, the viscosity constant B, and let us say I have attached a spring of spring constant K. So this is the spring which can oscillate up and down. This is our mass, and this is a viscous medium of some constant B, viscosity constant B. So as you know that the force which acts on this mass block due to the viscous medium is BV, where V is the velocity of our oscillator. So this is something damped oscillator. The damper extracts energy from the oscillating system, and to oscillate this system, to set it in motion, we need to apply some external force, some non-conservative force, some f of t downwards. And so let us begin this problem by using Lagrange. Now when we are doing such problem, first we need to choose what is our generalized coordinate. So the x coordinate, x, I choose x direction in this direction downward, happens to be Cartesian. Well, this is our generalized coordinate. How do we know it? Is it complete? Can it look at all the parts of the system at all times? Yes. Is it independent? Like, this is very simple. It can only oscillate to and fro, 1 degree of freedom, and there is only one coordinate we require to completely describe the system. So is it independent? Yes, because if you freeze x, there is still some movement. Is it holonomic? There is only 1 degree of freedom of the system. Way simpler. There is only one coordinate to describe the system. Yeah, it is holonomic. X is generalized. It happens to be Cartesian in this case. It might not be necessary for other types of problems. This is our first problem. Now how do we proceed? So I write that my Qj is basically Q1. I have only one coordinate to describe the system, so J becomes 1, and that is x. This is the direction of x-axis, vertically downwards. And let us write the total kinetic energy of the system. How much is it? Half m x dot squared. This is the kinetic energy of the system. And what is the potential energy of the system? What is our potential energy? V. Give it a look. Yeah, you're right. There is some potential energy due to the spring. That's half kx square minus the gravitational potential energy of this mass block, mgx. Right. This is the total potential energy of the system. Now this is the unstretched natural position of the spring, so this is our reference level, and from here we are measuring our quantities. We have got T, we have got V, we need to find L, the Lagrange, which is T minus V, Well, that approach can be applied, but we can do it in a more easier way. That is, we remember, if you remember what was 1, 2, 3, what were all those terms. Okay, give this a look. I'm going to rub this and we are going to proceed. The next step, how we are computing our terms 1, 2, 3, which form the LHS of the Euler-Lagrange, and how we are forming our RHS, that is the fourth term. So before that, give this a look. Yes, I hope it is complete. So let me rub it off. Okay, before I rub, so what is this f of t? Is it conservative? Yes, it's conservative. No, sorry, if this is external, it is doing some work on the system. It is making the system do some work. So sorry, this is non-conservative force, and by that I mean there are two forces which are non-conservative. So what is the net force on the system which is non-conservative? The sum of all the individual non-conservative forces. So I write that as the summation of all individual non-conservative forces. The FIs are the individual non-conservative forces. So those are now this is the I direction, I hat direction, right? So f of t I hat minus, this is the direction of b v, that is bx dot, v is x dot, so minus bx dot I cap. This is the net non-conservative force acting on the system. Non-conservative, because the damper will extract energy. It is non-conservative, a source of dissipation. The viscosity is the source of dissipation, and this external periodic force f of t, I'm going to describe f of t anyway. So that one is also non-conservative because it will make our system do some work, and hence it is non-conservative. And this is the sum of the non-conservative forces acting on our system. This expression is very important. Give it a look before I rub it. Now we will compute our 1, 2 and all those terms. So what is 1? Pause the video and compute 1 and match the results. As I have done. So 1 is basically d by dt of 1. The term 1 is basically d by dt of, I hope it's visible, yeah, d by dt of partial of partial of t with respect to partial of q dot I. This is general. Now in our case the generalized coordinate is x, right? So this becomes x dot. So what is derivative of partial of t with respect to partial of x dot? So we know t was half mx dot squared, so the derivative of x dot squared is 2x dot, and that half cancels with that 2, so we are left with derivative of mx dot, and that basically is again mx double dot, right? This is our first term. What is 2? The second term, it was minus of partial of t with respect to partial of x. And what does it turn out to be? Well, now you notice we have to find partial of t with respect to partial of x. Is t a function of x? No, t was half mx dot squared. X dot and x are different, so therefore this is simply 0. Our term 3, what was term 3? It was partial of v with respect to partial of x. Well, is v a function of x? Let's check. V was half kx square minus mgx. So what are we getting? This is kx minus mg. And what do we get by adding them? 1 plus 2 plus 3. That is our LHS. Is it visible? Yeah. This is basically equal to this stuff. This is what you get, our LHS. Okay, now we have to compute our RHS. Note it down before I rub it off. Yeah, so I'm rubbing it off. And now what are we left with? Our RHS. How do we compute our RHS for the Euler-Lagrange? RHS in this problem is not 0 because there are some non-conservative forces acting. So RHS cannot be 0. Obviously there will be a force expression along the generalized coordinate. So for our fourth term, what do we do? If you remember, I wrote this as equal to sum of all non-conservative forces, so this I hat minus bx double dot I hat, right? This is the sum of all the forces. Now first we need to find some virtual work done. And what is work done? Force dotted with displacement, and that force must have a direction and magnitude. Obviously it's a vector, and that force must have some component along the direction of displacement or other way around. So here we are denoting the virtual work done as partial W non-conservative, right? So what is that? It's basically this one dotted with dr. Now what is this dr over here? Dr is that small displacement, that it's kind of a del x. It is like a delta quantity, something like this, moving. Dr is the direction, it is the small displacement along which the system moves. So basically in this problem, dr is that small virtual displacement along which you will have some component of this sum total of forces, and that will give you, when you dot product them, then you will get this non-conservative work done. This is virtual work. And now in general, this dr is a function of the del j's. Like it can be del j1, del j2, del j2, j3, del j4. But in this problem, since we have only one such generalized coordinate, so this is simply del 1, x1 rather, del x1. And so this dr is in which direction? Give this video a pause and give it a think. So in which direction is this virtual displacement? In which direction? Think of it. Yeah, so it is obviously in the x direction. So we can write this virtual work done as something like this. There's an I cap and dotted with our dr is basically a function of this del j's. So del x I cap. Basically the system is moving up and down, so some small displacement dr will be along this x direction, and the variation of that is our dr, and that is along I cap, I hat, anything you say. So and this is equal to, now you do the dot product, I dot I, it's f of t simply into del x minus bx double dot I dot I, again the same thing. So you get f of t del x minus bx double dot del x, and this is equal to, let me take the del x common, so left with this term, and this is equal to your q. You remember that RHS we wrote q x dotted with our del x. This qx is the force, the total non-conservative force which is acting along this virtual work done. So now you just cancel this del x's on both sides. You get your qx, your RHS, as equal to f of t minus bx double dot. This is your qx. So what is our equation? Sorry, I think this will be a single dot. Double dot makes it b times acceleration, which is not a force. bv is our force. I was doing that wrong. So bx dot bv, kind of. This is the correction made. I was writing it wrong. Now this is the qx, so you just simply equate LHS and RHS to get the equation of motion of this type of a system. And in this case, the equation of motion turns out to be rather very simple, which was anticipated from Newton's laws. Basically, it is the equation of motion. So what's that? mx double dot plus kx minus mg is equal to our RHS, some oscillatory external force minus bx dot. You can verify it by using Newton's laws of motion and Newtonian mechanics, and the result comes out to be this. Now one thing to note here is that this is the acceleration times mass term, the force, this is the spring force, this is the force due to weight. These two forces are conservative in nature, whereas this is the net acceleration of the system. These two forces are non-conservative in nature, and it is very much consistent with what we could get from Newton's laws, right? So this is to be noted. We could have foresee these expressions before getting into this equation. So this is the final equation of motion of our system, which is a mass spring dashpot system. The dashpot means that viscous medium. Now we move on to our second problem, which will be simply an Attwood machine, one pulley and two masses. So this is the second problem, the Attwood machine problem. So you basically have fixed ceiling, one pulley like this. There's a mass m1, this is m1, there's a mass m2, right? These gravity guys are downwards, some tension like this, right? We are not concerned about those forces anymore. So how do we proceed by solving this problem? Think of it. I will give the solution to this problem. Like, the problem is that you have to find the equation of motion of this system without using Newtonian mechanics. You simply use the Lagrange method and solve the problem. So in the next video, I'm coming up with the solution to this problem. It's pretty simple, and you can cross check it by using that Newton's method. You draw the free body diagram, whatever you used to do. You can actually, most of the JEE aspirants remember the direct result of this one, but as such, using Lagrange, we get a deeper insight into solving this type of problems. And the third video will be, in this problem session series, will be something very complicated and much more advanced than all of this. These are to illustrate how we are working with the variables and functions and how we are solving the problems. So thank you. The problem was to find the equation of motion of this system. The pulley has no mass. Only the masses of these blocks are concentrated at the center, and everything is having its usual meaning.